Which one?
40 maybe?
40? It's on 2.6, right? So an airplane flies at an altitude of 5 miles toward a point directly over an observer. The speed of the plane is 600 miles per hour. Find the rates at which the angle of elevation theta is changing when the angle is 30, 60, 70. Okay, so let's see. An airplane flies at an altitude of 5 miles toward a point directly over an observer. So they got a nice little figure for you. Yes. We have an observer down here. Then we have a plane over here. Pretty good plane. And the plane is flying at a 5 miles, 5 mile altitude, right? So this distance right here down to the ground is 5 miles. And I believe the implication is that it keeps that altitude always, right? An airplane flies at an altitude of 5 miles toward a point directly over an observer. So it's flying at 5 miles, and it's going to keep going until it gets directly above this observer guy. Right? So the plane's going in this direction, staying at an altitude of 5 miles. We'll go ahead and make a triangle here. And then, what else do I know? The speed of the plane is 600 miles per hour. Find the rate at which the angle of elevation is changing. So the angle of elevation is how this angle here from a horizontal to this line of sight. So that's labeled in the diagram as well. So what we have to do is first, what are my variables? What's actually changing here? As this plane flies this way.
Theta.
Theta is going to change because this hypotenuse is going to get higher, and so the right triangle is going to change. Theta changes.
X.
Yeah, let's go ahead and label this length x, right? Because this length is going to change as the plane flies. So x. And actually, the hypotenuse changes as the plane flies over as well, but we don't need it, so I'm not going to label it a variable. So now, the only piece of information they gave us, besides the 5 mile altitude, is that this plane is flying at 600 miles per hour. Well, and then they gave us theta eventually. But what's this 600 miles per hour going to translate to, do you think?
dx over dt.
Now, yeah. So that's one piece of information that I know. I want to eventually figure out what d theta dt is because it asks me how fast is theta. Find the rate to which the angle of elevation is changing. Let's just do part A. Right. So for part A, it gives me theta equals 30 degrees. But I don't do anything in degrees. So now I pretty much label all my information. Now I have to set up the formula. I'm trying to get at d theta dt. And I have information about this distance and this, not this distance exactly, at least not yet, but I have a rate, right? I have a dx dt. So when I set up my formula, I want something that relates theta, x, and phi.
So katsua?
Yeah.
Tangent?
Tangent. So the formula I want to try to use here is that tangent of theta, right? Tangent is always opposite over adjacent. Tangent of theta should equal 5 over x.
So do we search for x first before we keep going, or do you want to keep it as a variable?
You could go either way. You could go either way. You're going, the way we set it up, you are going to have to find x eventually. But when you do the derivative, you want to keep it as a variable. So let's go ahead and do the derivative first, and then we can come back and solve for x later. So because I'm looking for d theta dt, I'm going to go ahead and put in a ddt on both sides. The derivative of tangent is, now be careful, right, because the derivative of tangent is secant squared, but then you have to multiply by the derivative of the inside. So times d theta dt. Now, because of the way we set this up, we kind of made more work for ourselves.
We'll rewrite it to 5x negative 1.
Yeah, this will be 5x to the negative 1. Alright, so 5 over x is equal to 5x to the negative 1. So then when we do the derivative, this becomes negative 5x to the negative 2 times dx dt.
Okay.
Right? When you do this derivative with respect to t, or this guy here, I guess, sure, you do the derivative of the outside function, the negative 1 comes down and it changes to a negative 2, but then you have to multiply by the derivative of the inside. So this guy's going to get a dx dt. Now, I'm going to clean this up a little bit because it's annoying. This x is going to go on the bottom, and then this will be dx dt. Okay, so what? What am I looking for? D theta dt. This is my unknown.
So we'll divide by secant squared.
What do I know? I know theta, right? So I know this is pi over 6. I know dx dt. So as soon as I figure out what x is, then I can plug it all in and divide over the secant squared. But I am going to need x in this case, the way that I set it up. So, how do I find x?
Algebra.
Algebra. So what formula am I going to go back to solve for x?
So you don't want to divide by secant squared.
It's just going to, I mean, you can, but it's not going to help you until you get this x.
Okay, then we'll isolate it and solve
Tangent
it.
of pi over 6.
Yeah, absolutely. But we have two unknowns right now in this equation. D theta dt and x.
We'll replace
So-
pi over 6 on secant.
Yeah, but what I'm saying is we still have two unknowns, d theta dt and x. So I need to solve for one of them somewhere else. Right? I don't know this right now. So I don't want to work with this equation until I only have one unknown. So I want to get this as my only unknown, so I'm going to come back and solve for x in a different equation. Namely, I'm going to use the fact that tangent of theta is equal to 5 over x. And then I know that theta is pi over 6. Tangent of pi over 6 happens to be root 3 over 3. And then you can solve for x here. The x will come up. The 3 will come up. So root 3 times x equals 15. Divide by root 3, and x is equal to
5 root x.
15 over root 3. Yeah, you can simplify this a little bit, but it doesn't matter.
And
So
now
now I have x, which means this guy is a known. So then I can plug in here, 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 and isolate this. So I'll do secant squared of pi over 6 times d theta dt equals negative 5 over 15 divided by root 3 squared times dx dt, which is 600. And then you actually have to calculate what secant squared of pi over 6 is.
Oh, 4, sorry.
I don't think it is, though. I don't think it is. So where's pi over 6 on a unit circle? Let's see. So here's unit circle. Here's pi over 6. 1, 2, 3. 1, 2, 3. 2, 2. So cosine at pi over 6 is root 3 over 2. So secant is the reciprocal, it's 2 over root 3. So this guy is going to become 2 over root 3 squared. Theta dt, I'll solve for eventually. What happens here? Negative 5 over, this looks like 225 over 3. All right, go ahead and square it out. 15 squared is 225. Root 3 squared is 3. And then times 600. Remember, this is, square this out too. This is 4 over 3. D theta dt. Oh, what happens here? Negative 5 over 225 divided by 3. This guy's going to flip up. So it'll be negative 5 times 3 over 225 times 600. And it's just kind of boring stuff. So let's see, 5 probably goes into 225. 45 times. So then you have 3 times 600 over 45. So you could do this in a calculator, right? It's like 4. Oh, what happened to my equal sign? My bad. So then I have to do this. What is this? 400 or something? 40.
It's negative though, right?
Yeah, I had a negative here. Multiply up to 3 divided by 4. So 120 over 430. I'll ask for questions. We made our life actually pretty hard right here.
Mm-hmm.
And I'll show you why. You can tell me why in a second. But this equation makes sense. This, you see, this is the equation we need to use. Deriving it is okay. Kind of, I think the hard part here is one, solving for x, right? Because you had to go back to the original equation to solve for x, and that you might not have thought of that. But then also all these numbers, you just got to keep track of the fractions. But any questions before I show you a slightly easier way to do this? It's okay? You see it, it's okay?
Now I can relate between the problem.
What I probably would have done if I were just sitting in my office trying to do this, instead of using tangent of theta, I probably would have used cotangent of theta. You see how that simplifies things a little bit?
Still in self for x, right?
You get rid of the x, right? Because if you set up cotangent of theta, cotangent of theta is the reciprocal of tangent, so it'll be x over 5. And now you have your variable on top instead of on the bottom. So now this will be cotan theta equals, think of it as 1/5 x. So when you derive both sides, derivative of cotangent, well, that's not much harder than the derivative of tangent, right? I mean, it's negative cosecant squared theta. Right, derivative of cotangent is cosecant squared, negative. And then the derivative of 1/5 x is what? 1/5. Yeah, derivative of 1/5 x is usually 1/5, but because it's with respect to time, dx dt. So So we managed to derive away our x, which didn't happen last time because x was on the bottom. But here, when x is on the top, we just are left with a dx dt, so now we can plug in 600. And then we can plug in pi over 6 here. It should work out. It should work out. Oh, except I forgot something
You
when I
should
derived.
multiply times theta over dt.
Yeah, that's a good check, right? If you're missing the thing you need to solve for, you probably screwed up. So yeah, when I drive cotangent, it is cosecant squared, but I need a d theta dt because of my